Okay, so this is test 2, part 2, the second question out of the 3. And so it's question number 5 on this particular exam, which is a no calculator question. And this is at the beginning of 2010, a landfill contained 1,400 tons of solid waste, which is a lovely thought. The increasing function, W, models the total amount of solid waste stored at the landfill. So increasing function kind of feels like a throwaway line, but maybe we'll use it. Tough to know. Planners estimate that W will satisfy the differential equation. So they've got this differential equation modeling the rate of change for the next 20 years, so till 2030. W is measured in tons, and T is measured in years from the start of 2010. So again, not sure all of that information is actually going to come into play. They've given a few different things. But we'll see what it does. So part A, use the line tangent to the graph of W at t equals 0 to approximate the amount of solid waste in the landfill that the landfill contains at the end of the first 3 months of time. That's interesting that they gave this little parenthetical t equals 1/4. Certainly 3 months is a fourth of a year, and you have to be ready to make an adjustment on units. They don't often actually give you the explicit adjustment on units to make, but here they did, so nice of them. Perhaps to deal with the shock of a solid waste landfill. So let's see, we've got first 3 months of 2010, and we're going to use a tangent line approximation. Well, let's see, a tangent line approximation, that looks like this. So we've got y minus y1 equals m times x minus x1, and we're looking to draw a tangent line at t equals 0. So at t equals 0, let's see, well, at t equals 0, I'm going to put in a 0 for time, which is x, so x minus 0. Slope, we're going to have to compute slope, so I'm going to have to figure out what that is. And then y1, which is the W amount, the actual amount of waste, they're giving you that piece of information. So they're telling you you got 1,400 or 1,400 tons in there to start. So y minus 1,400. And then our slope, we're going to need that 1,400, plug it in to get the slope. So we're going to do 1/25th 1,400 minus 300, so that is 1/25th of 1,100. So 1,100 divided by 25 by hand without a calculator, we can do it. Just got to be brave, so here we go. If we, let's see, 25 goes into 100 4 times, so there are 11 sets of 100. And I've got, out of every one of those sets of 400, I've got 4 25s, meaning this is 44. There are other ways to do that division. But again, my thought process there, I know 25 goes into 100 4 times. I'm then thinking, okay, there's 11 sets of this that happens, therefore 44. You could longhand division it. And in truth, this year on the exam, you can use a calculator to do computations, and they're okay with that. So any way you slice it, 44 is our slope. And that's just at this moment. That's at t equals 0 when we've got 1,400 tons. That's it in terms of a tangent line. You can certainly write it y equals mx plus b if you want. You don't have to, and I actually wouldn't here. You're going to pick up a point for the tangent line, and then we're going to pick up a point for the approximation. So the approximation, and the reason I say not to do it, is we're going to plug in a 1/4 for t. 1/4 times 44, I know that easily. I don't need to mx plus b this thing. That's just an 11. So I've got y minus 1,400 equals 11. So y equals 1,411. So what that's saying is this is an estimate, but that is 1,411 tons of solid waste. So tons of solid waste. Again, not a fun thought, but so be it. And that gets us a point. So that's part A. You get a point for the tangent line approximation. You get a point for the estimate, which is the 1/4 of a year. And then part B actually draws upon that estimate. So it's saying find the second derivative and then use the second derivative to say whether what you got in part A was an underestimate or overestimate for the amount of the landfill at a fourth. So let's see, part B, finding the second derivative. Well, if we've got a first derivative, we've got W prime. If we do W to prime prime, or the second derivative, I've got, so my second derivative, if I take the derivative of W prime, I get W prime prime. And then if I take the derivative on the right hand side, let's see, that actually is going to be easier for me So I'm going to do an aside up here. I'm going to say dw dt equals, I'm going to distribute that 1/25th through. So 1/25th when it hits 300, that's 3, like I did down here, that was 11 sets of the 4. 25 goes into 100 4 times, so it goes into 300 12 total times. So I'd have minus 12, and then 300 divided by 25 is 12. So that is actually the thing I'm taking the derivative of. So I've got 1/25th times w prime minus 0, because when you take the derivative of 12, that goes away. W prime is this expression. So I know W prime, they gave that to me. So it's 1/25th times 1/25th minus W times 300. You've got an expression for W prime. I keep wanting to say W prime prime, the second derivative of W. You certainly can rewrite this thing. You can do 25 times 25. There's no harm in that, and you can put 25 squared on the bottom, or you can compute 25 squared. That's fine. You don't have to, though. And we've got W minus 300. And we want to know what it's worth at t equals 1/4. Again, what I like about this is they're making you jockey back and forth, not just between units, but between measurements. If you plug a 1/4 in here, which would be a common error, that entry, that W, is not time. That is amount of solid waste, which at 1/4, if we want to know if we've got an over or under estimate, we're plugging in the actual 1400-ish number. So again, regardless of what the values are, we know that they're going to be that's going up. It's an increasing function, which actually now all of a sudden that makes sense why that's there. I've got an increasing function. I don't actually know what W is. I have no way to get it. I know it starts at 1400 and it increases, which means the numerator here is always positive. I'm not dropping low enough that I'm going to go below 300. And you could use common sense on that because you're adding to a landfill, but specifically calc-wise, they're using this increasing function bit. So that means this second derivative expression is positive. So this is positive. And therefore, I'm never sure how to spell therefore if it's F-O-R yet. It feels like F-O-R. No, I don't know. Good question. Somebody can correct me on that. You wouldn't get nailed on the AP for it, but therefore, in the moment, I can't see which one it is, if it's an E at the end or not. So we're going to just cross it out and go therefore, which feels wrong. So that's positive. Therefore, W is concave up. And the estimate in part A is an underestimate. And the thinking there is if we've got a concave up graph, we've got a graph that's concave up. Anywhere you put a tangent line, it's gonna be below the graph, except at the point of tangency. So as we move forward and make an estimate off it, we're gonna be below the actual value. So it's an underestimate. So again, I like this because they're really making you think abstractly with these different pieces of an increasing function. We've got concave up, and then what does that mean about the estimate? And so the 2 points tied with this. You get a point for the second derivative expression, and you get a point for the analysis. I'm saying that it's an underestimate and why. And then the final one is a 5-point piece, and it's a really straightforward separable differential equation. So we've got dw over dt is 1/25th w minus 300, and let's separate that. So dw dt equals 1/25th w minus 300. So I've got dw divided by w minus 300 equals 1/25th dt. That's just doing our grouping of variables together. So this is part C. So that's separating. You get a point for separating. We're then going to integrate this thing. You can do a u substitution. So technically u is w minus 300, or you can recognize that this is an implicit u substitution. So I've got ln w minus 300 equals 1/25th dt, or sorry, 1/25th t plus c. You get a point for the antiderivatives, you get a point for the plus c. So we're just racking up points. We then need to plug in some sort of initial condition, and that's this one. And they reiterate it here, but at time 0, Our waste is 1400. That's the most interesting zero I've ever drawn. So t equals 0. We've got waste is 1400. So I'm going to use that to solve for c. So 0 goes in, that zeroes this thing out, plus c. And then I've got ln of 1100, and that's my c. So c is, I'll formalize it here, ln of 1100. So I've now used my initial condition. I get a point, which means that the final point is just isolating w. So the very final point in the problem is we're going to say, okay, now let's take this thing, and I've got my 1/25th t plus the ln of 1100, and really I don't need absolute values on that due to the fact that 1100 is positive. And actually I can drop the absolute value bars altogether, which we're going to need to in a minute here, because we know it's an increasing function, starts at 1400, which means this thing inside the absolute value bars is always positive. So I can drop that off, but and it's not a big deal on this particular one. So I'm going to e both sides. So I've got e. So it's e to the 1/25th t plus e plus ln of 1100. And I'm going to wait just for a moment on adding the 300 over, because if I have e to two different powers, I can write that as multiplication. All right, so I can write that as e to the 1/25th t times e to the ln to the 1100. That's what it means to add in the powers. It means I'm multiplying the bases. So e ln of 1100, that gives me just an 1100 multiplier out front. And I'm going to write t over 25 instead of 1/25th t. And this is just a cleaner way and more compact way to write your answer. Technically, it's free response, so they should give you credit as long as you have an equivalent expression, but you should also be able to follow through the steps of moving things around to get w all by itself and pick up the solitary final point. So that is an expression for the amount of solid waste in the landfill at any point in time from 2010 all the way up to 2030. The landfill just keeps on filling. So that is our problem. And there it is again, second part second question out of the three on the second part. The other two are on the solution sheet.